Good day to everyone. My name is Alexander Chinaya Flores, and today with Benoit we will make a presentation of the current state of FloRaSat 2. The title of the presentation is FloRaSat 2, Simulating Cross-Linked Direct-to-Satellite IoT in LEO constellation with joint access and routine evaluation. It's a very long name, but basically we will present the new models that we developed in the simulator and how we integrate with the previous models. First, let me talk about the agenda of the presentation. In the first topic, we will talk about, so we will give some context and motivation. Then we will present the evolution of FloRaSat, of the simulator. And then we will give some details about the models that we developed with the previous one. And after that, we will talk about, we will present some tutorial and a use case. And basically, we will present how the functionalities works. And additionally, we will also present a conclusion section. And after all this presentation, we will make like a demonstration in live where we can see how the parameters are set in, how the modification of these parameters affects the simulation per se. That will be all of the presentation. Okay, first. FloRaSat is an open source end-to-end event driver simulator tool that was developed using OpNet++. And this kind of tool is more focused on DTS, IoT scenarios. And in order to understand the importance of this kind of tools, please let me give you some details about DTS IoT. As we know, the main feature of DTS IoT is the direct connection between the devices and the satellites. And based on that, in order to have a global coverage and continuous connectivity, the deployment of several satellites, in this case we are focused on LEO satellites, we need to deploy several satellites to create a constellation. So in this way, we were able to create a global continuous connectivity. So these features make FloRaSat a good alternative for scenarios, for example, where a quick deployment is required. For example, like it can be a disaster response, and also it's also a good choice for scenarios where a low density of devices occurs, where the implementation of terrestrial gateway is not viable. So based on this, we can have, of course, this is an area that in recent years has gained a lot of importance for the research community and also for enterprises. And we can highlight that there are several main actors that are working currently in this kind of technology. As we can see in the image, we have Kineis, we have Y, we have FOSA, and between other companies. Since we already know what is FloRaSat, I will give you now what is the difference of FloRaSat between other alternatives that we found.
One question.
Yeah.
Can you go to the previous slide?
Yeah.
So just to be clear, at this point, you also guys are considering narrowband IoT?
No. It's only the technologies that are working on DTS IoT. But we are FloRaSat is based. It works with LoRa.
And future work narrowband?
It is in the roadmap, but modeling NB-IoT is not an easy thing.
It's kind of
how long is the road?
I would say long enough.
Yeah.
Long enough not to pitch it so much at this point.
No, the thing is how many people do you need to work on the development of the things?
I think first what I would try to do is an assessment of what models exist for NB-IoT and check if it is worthwhile to integrate this with FloRaSat. That would be my approach, not start to implementing things.
No, there's something about the project on that specifically.
Yeah, I mean, it was, I guess, a few, 2 or 3 persons would be ideal, but I think it's quite sophisticated. If you want to model NB-IoT from scratch, that can be quite challenging.
Okay.
It's a cellular system.
It's a cellular system, and it's integrated with the LTE waveform and so on. So it's.
But I don't remember if OpNet++ has already something.
There is something for LTE, and there are some early creation of NB-IoT module for the LTE library.
Yeah.
But we will need to understand what it takes to bring that into FloRaSat.
Yeah.
Okay. Following. Since we already know what is FloRaSat, now I will explain the big difference of FloRaSat against similar alternatives that we found in the literature. Here we focus especially in four main aspects. The first one is if they support orbital propagator, if they support a packet simulation, if they are focused on DTS IoT scenarios, and if they support a constellation grade. We found several alternatives, and until we know, FloRaSat is the only tool that is capable to satisfy all these aspects that we are considering. With this in mind, now I will in the image we can see a graphical representation of the architecture of FloRaSat. The gray boxes here, they represent the original models that were introduced in the first version of FloRaSat. In the slide is orange, but here in the screen is pink. But the pink boxes, they represent the new models that were introduced in this new version. As we can see, we have new models like Constellation Creator, Topology Control, the Routing Sandbox, the Event Manager, and the Statistics. We will give some details about them later. And we also have the green box, which is not that is not a module per se. It's more an indication that in this version of work we also implemented a new MAC protocol that is called KeyMAC. Okay, with all this in mind.
Sorry, one question there. Okay, are you going to explain what's KeyMAC here?
Yes, okay. We will also explain in the next slide what is KeyMAC and how it works. Okay, I will detail some the main modules that we're introducing. First, we have the Constellation Creator module that basically is the module responsible for the creation of constellation. And of course, this module supports a Walker Delta and a Walker Star notation. Using this model, we were able to create complex constellations like OneWeb and Starlink, which comprise hundreds or even thousands of satellites. It's important to highlight that the positions that we obtained using this constellation were validated against the position that we took from STK, which is a very widely used tool. And additionally, we also have a topology control module that basically is responsible for to manage and keep the topology of the constellation. This module basically manages the communication between the satellites and the ground modules, the ground station and other stuff. And additionally, this module, of course, continuously updates the inter-satellite links and also the ground satellite links. We also have the Event Manager module. This module basically activate or deactivate the inter-satellite links. And in this way, this module is also responsible to test the adaptability of the routing algorithms to scenarios of failures and congestion, and how these routing algorithms overpass these kind of situations. And finally, we have the FloRaSat CLI module. Basically, it's an external module, as we saw in the previous slide, that is not developed in OpenNet++. It's more developed using Python, but it's fully integrated. And this module is focused especially in create some metrics and visualization to compare the performance of some routing algorithms. This module supports an easy integration of additional graphs or additional metrics.
A question over there. OpenNet++ was originally developed in C++.
Yeah.
As far as I can remember. And all the modules here are also developed in C++, and or there's a kind of link with Python or whatever.
The only module that has a connection with Python is FloRaSat, FloRaSat CLI, but the other one is developed in OpenNet++.
Okay, thank you.
Okay. The other main incorporation that we have in this new version of FloRaSat is the routing sandbox. That basically is a sandbox that facilitates the integration, the creation of new routing algorithms. Mm-hmm. For this sandbox is based on an abstract class that we call it routing base. And of course, there are several functions that can be overridden just to implement the desired behavior of the routing algorithm. And using this sandbox, we were able to implement 3 routing algorithms: the directed routing, DDRA, and disco route. This last one is a routing algorithm focused for mega constellations like Starlink. This is all this work was already published in a previous paper, but after that we already work in some more features, and that's how we additionally for this presentation we were able to integrate the MAC protocols functionalities with the routine module that we described before. The idea of this is this integration provides FloRaSat the ability to consider several constraints, like can be the packet loss, like can be congestion, like can be latency. So in this way, FloRaSat can choose the best routing path. So in order to optimize or choose the best the routing path actually. Basically, the process of the integration is it can be somewhere the result, the message that is transmitted to the satellite after the integration. We can see a representation of the package in the image, where basically we have the 4 sections. The first one is the corresponds to LoRa T, some details of the physics layer. Additionally, we have a MAC frame that has information about the MAC protocol. Then we have the routing header, where basically has information about the route that we choose at the beginning of the transmission. And finally, we have a section that has information about the application process. After that, additionally, we also implement the KeyMac protocol that Benoit will explain later.
Alex, one quick question before you move. In that slide, the routing header is added by the device or by the satellite?
And the device.
Okay.
The process of the routing choose starts at the device at ground, and using that information is sent to the satellite, and inside the constellation is chosen the next path.
So the device decides which satellite to send the first the first hop, or that routing header also contains the last hop or the destination hop. What does the
the routing actually is work in that way, in the first way that you mentioned it. Okay. We find a pair of satellites, which is the first satellite and the last satellite.
Okay.
So the device transmits to all the nearest satellites around the device, and when the transmission is reach the correct satellite, it detects that is the satellite, the first satellite, and then trying to find the best satellite to reach the final satellite.
Okay.
So that's how it works.
The calculation is done in the device itself.
Yeah, the calculation is done, but the transmission starts from the device, and it transmits to all the nearest satellites around the device.
But the first satellite should be one of the satellites with survival.
Yes.
So it transmits to everybody, but only one will respond.
Only one will respond, and only one will be able to transmit to the next.
Okay. Okay. Cool.
Because I guess this is a bit replicating what LoRa does, right? All the gateways receive, right?
Yeah.
And then in this case, based on the information in the routing header, only one gateway will keep forwarding the packet to the ground station, and the others will drop it.
Because they don't match the address.
Right.
Okay.
Right.
Okay.
That's a bit hard-coded because of how the routing was designed in the first place, but I guess this could be, generalized a bit more. Maybe we also want all gateways to forward a copy.
Yeah,
that would be one idea. Also, I mean, in practice, we don't want the device to compute the route. We want the device to be as stupid as possible and just uplink the packet, and then the receiving satellite decides what to do with the packet.
Yeah.
So to replicate a bit more what's happening in real networks, that routing header should be added by the receiving satellite, right?
Yes.
But yes, this is kind of like a bit first iteration.
It's important to highlight that.
But the last satellite, going with this way, you calculate that also all the you decide which is last satellite and which is going to go downlink to the base station.
That's calculated at the beginning of the transmission in the device.
This way. Okay.
But doesn't that depend on the routing algorithm?
Yes, of course. That's why it's chosen from the beginning. Okay. But it's chosen from the beginning. It depends on the routing that you are choosing, the routing algorithm.
Yeah.
But the calculation starts on the device.
So because there are some routing algorithms that you decide the full path and the destination on the source node, and there are other routing algorithms we will also use, like Disco route, that they compute on a hop by hop basis.
Mm-hmm.
So this depends on the routing algorithm you choose.
Okay.
Yeah. So when you say that you prioritize less congested path, you are using one of what this one, the source routing or the other one?
We are not giving more priority to less right now, but this integration has the potential to consider. Since we right now the routing algorithm will work together with the max functionalities, so he will know which path has more congestion, so he will choose.
So enables. It's not okay. Good.
Well, the next.
Okay, so as Alex said, we implemented this whole frame for each packet, and our goal was to try to benchmark our new end-to-end system. So for that, we used a new MAC protocol that is trying to, like, it's written to enhance the probability of successful delivery. So what happened is that you wanted to send one packet, and we will have multiple parameters. We have the first parameter which is the time to start transmission. So when you have a packet, we will wait a random time before sending the first packet. Then we have the time between transmission. Yes, I didn't say it, but each packet will be retransmitted n times.
Mm-hmm.
So I wanted to transmit. I said, okay, I will do it 5 times. The first parameter is that, okay, I will wait some times before transmit the first one. Mm-hmm. Then I will wait another random time between 2 transmission. And then until when I finished, I will wait a random time between sending the next message. And depending on the constellation and on how we distribute our devices, we need to change and to define those parameters in order to get the best results. Because more, for example, if we have more repetition, we can send less data, and we spend a lot of energy trying to send the same data. But if there are a lot of devices, maybe it's important to have a better delivery ratio. You have to have better, like to have more packet to arrive to destination, because it will implies to have a more data flow in the full scenario.
So do you have a kind of a paper kind of looking at the trade-off of those parameters?
No. For now, we just have a paper that is like an overview of what we can do in FloRaSat. This KeyMac was originally like a test bench for Kineis. Mm-hmm. So they wanted to see what happened if we use this kind of MAC layer in their network. So I work at the beginning with their constellation and their ground station, the real one, and try to make some statistics for them with this particular.
So it's not necessarily it's beating other maps necessarily. It's just for the Kineis. No?
For now, it's just a test for the Kineis, because they use this. And they wanted to have a result for this specific parameter, because they are using this right now.
And it's better than Aloha, for example? Much better than Aloha? Or
I don't know if they have some statistics about it.
We don't have results for that. I mean, there is the journal extension that we submitted. Yes. So this is a journal paper that we can share with you, which is the analysis of this. Yes. But I mean, you see, it's quite drastic, right? It's just repeat just to maximize the delivery, but you also ingest the uplink, right? By doing that. So,
but the good is the Kineis.
This is a Kine, yes.
So you can have an excuse that is industrial or like exist or something like that. So
yes, but unfortunately, it's not public. It's not something that you can defend publicly.
I thought it was okay.
This is a MAC layer, but we don't. For the paper, we don't use the Kineis.
We don't use the Kineis world.
You don't say that.
It's a private stuff. But so the math
Simulation.
mechanism,
Yeah.
it's a bit like, I mean, it's a bit stupid if you think about it.
Yeah.
But
Sometimes
the
it
trade-off-
works. It simple works.
But it works. I mean, the good thing is that this is what industrials are doing in practice at some point,
Yeah.
right? So that's the baseline, and from there you can grow and see what you can do better.
Yes. So yes, it was just to have like a fun Mac layer to to show what we can do in FloRaSat.
So the thing is, you decide from the source which kind of alternative you use from this.
Yes.
Okay. So, but it doesn't affect when the thing is the receiver will be congested some way or not, okay, depending on that. But it won't. There's no
Adaptive thing.
no arbitration or nothing.
No.
Okay,
In fact, the goal of Kinesis was to test everything and to pick the best one for each the place in the world. For example, let's say in France, maybe 2 minutes here and 2 minutes here, it's good. Maybe if you are more in the north or more in the south, the parameters can be different. And they are set at the beginning.
Because of the density?
It depends on the density, and also it depends on the constellation, because they have like a constellation that prefers the poles, because this is like a star constellation. So yes, we have more transmission windows, more we are the north and the south. So the parameters could be different. So this is why I was working on this specific KIMAC for them. But it's dependent on FloRaSat. I use FloRaSat for that. Yes, so now I will just show some videos of each steps of FloRaSat is working. So just we are using a Iridium constellation with 66 satellites, 20 ground station, and 20 devices. So it's nothing of Kinesis. It's 20 ground station around the world and 20 devices that we put randomly. We use the DDRA routing. So yes, what is good with this new version of FloRaSat is that we can use ISL links, routings, and also MAC layers, so we can test everything. So the end-to-end from the device to the ground. Okay. So the first step in FloRaSat is to initialize all the nodes. So you can see each time a node is in red, the node you can see it. It's doing the initialization. So the parameters are set up. Okay, I can do it again maybe. Yes. So the parameters are set up and everything. So it's not the same initialization for each node, but each node goes through this initialization process. Okay, then we can check the routing functionalities. So for example, we can see here, this is a device that will send to a satellite, and here you can see that there is the route that is written. So the route is this route here. So the route is written, is displayed by the satellite to see what will happen for this specific packet.
You run the video again?
Yes. So the node is
it transmits to the nearest
transmit
satellite.
to the nearest satellites, yes.
And only one.
Only one.
Reacts
Because
to it.
it was the gateway chosen by the device to transmit this specific packet.
But the physical layer allows you to reach multiple satellites.
Yes.
But this is why you see the red line moving to 2 satellites at the same time.
Yes, I can make it again. Those 2 satellites are in range of this device, but this one was chosen to do this route to reach this ground station.
So the device also has a journal, so it has the whole knowledge of the satellites to define the route.
In this particular implementation, they know the nearest satellites.
Okay.
So they can.
Yeah, there is a module that has all the position of the satellite.
But the device
has access to
that module. Okay. It's a good view. Okay.
And just question to make sure, in real life, that there is a model that does that, right? It's not an assumption.
I think in real life, you won't have a device that knows the full network. They don't have a God mode access
But
to
you
it.
can
It depends on
predict.
yes, you can get some partial knowledge of what's happening.
Yeah.
I guess so. For instance, this is maybe we can discuss later, but in practice, you will have a satellite that will beacon out something, and based on the receive beacons that you get, you might be able to understand which is the best one because of the receive power or something.
You can filter.
And I guess that is the limit of the knowledge you will have. And then this is why you will just try to fight for the uplink, try to get there. And once you get to the satellite, it's up to the network to see what happens. So this is, in this simulation, it's a bit unrealistic that the device will do. It's optimistic. This is the point. It's
But
optimistic.
the thing is, and then the aim here is to reach a base station.
Yes.
Okay, so the routing algorithm, that only satellites will choose which is the closest or the best route to arrive to the nearest base station, and then goes to the ground network and so on.
Yes.
The fact is, the routing modules were not designed by us, so they are working like this. So we're trying to implement to work with it. So because the route was chosen on the device, we keep it because otherwise we
can play with the map, not playing with the route.
It's just that we need to redo everything.
Okay.
So we keep it because it works.
No,
but the thing is, it's an optimistic decision, right? It's like a global optimum because you really choose the best route all the time. In practice, if you really split the routing responsibility to the satellite network and just leave the device stupid, then you are not really being global optimum, but you are being more realistic. So, yes.
In fact, it depends on the routing scheme. So here we use DDRA, but like one side, it depends on the routing scheme. Okay. Okay. So now we will observe some collisions. What happened is that the device here, voilà, we will have a collision here because this device and this device here wanted to transmit to the same satellite. In fact, this is the first repetition. So both wanted to transmit data at the same time. They have random time, but the random time is not enough for them to not have a collision here. If we quickly go to the second repetition, this is the same thing. We will have the same thing that will happen here. Whereas the first one is transmitting, and the second one is transmitting at the same time. No, this is not the same repetition. This is the second repetition of the KMAC protocol. And there are still a collision here. But something which is good with the MAC protocol is that we have another transmission. So same thing here. We still have a collision. Yeah, we see this is written collisions. But if we go to the fourth repetition, this time random times is enough to don't have collisions. So the first one is transmitting here. The transmission is finished, and he will transmit later. So we don't have transmission. So for this fourth repetition, the packet, so the information gets to the constellation and then is routed through the network. Okay, so what happened is that we evaluate the performance of the KMAC layer with the routing scheme. And we use specifically this Iridium, the full Iridium constellation, so this is 66 satellites and 288 devices. So the devices are spread across the world equally, so they all have the same area on Earth. So they are so this is like to create a kind of heat map, for example. But in this specific analysis, we only get the final analysis on the final node. We will see this later. And then the objective was to know what will happen if we increase the repetition on the MAC scheme. So is it very interesting to have like 12, 15 repetition, or is it one or two enough? So in those plots, we have the IS cells and the non-IS cells. So it's important to note that the non-IS cells are like the satellites are acting like store and forward node. So they get the packet, they keep it, and when they have a ground station inside, they send it. So what happens is that if we have low repetition, without ISL is better because we have this issue of choosing the right satellite to do the routing. So if the packet is not reaching the satellite wanted, the packet is discarded. So a lot of packets are discarded, but without ISLs, no one's know. It just takes the packet and try to deliver to the nearest ground station. But then what happened is that we increase the number of repetitions, and the ISL case became better and better, and the without ISL didn't become better because, for example, the queue is full, and we lose packets. And without ISLs, we don't have queues because the packet is transmitted directly. And this is the same graph. Just here it's percentage, and here it's.
But the big question is worth the difference. So the thing is, at the end, okay, after 12 repetitions on the okay, they're almost close. They're really close of there.
Yes.
Which one would you choose? Not taking the first.
If you, yes, the fact is, I have other graphs to show.
Yeah.
But for example, if we have an ISL constellation, only one.
Only one repetition, it's a problem again.
But I mean,
after 5 repetitions,
yes,
everything goes smoothly.
Yes, so we don't have to add more repetition, and we even don't need ISLs. But ISL have other advantages. We will see later.
Okay.
So now this is a little more complicated because before it was messages. So when you want to send data, the first, I didn't explain this. When a device wants to send data, you want to send a message, but you have 5 repetitions. So this is 2 different terms. So this is a messages. So this is the information that reaches the end to the ground stations. But now we are looking at the repetitions. So the individual repetition for each messages, we are looking at how many of them are received. Because what happens is that for the same message, if I receive all the repetitions, I have 5 times the same information. So it's not sometimes very useful. So what happened here is we see that we receive a lot of repetitions with ISL, without ISLs, and the issue is for this red one is with ISL received by the root per satellite, so received by the good one. So what happened is that the good satellites don't receive the packets every time. So it's for that the delivery ratio of messages here is less important because we receive less messages, less repetitions. And here is the number of collisions. So for sure, if we have more repetition, we have more collisions because we are generating more traffic. So this is more.
How many devices are transmitted there?
288.
Okay, and the 288 before you said, okay, mentioned.
Yes.
But with 288 transmitting 5
times.
5 times?
There are 5 packets, 5 messages, 5 messages, 5 times.
5 messages, 5 times. You get in what point here? There are 5 repetitions, okay, and then, okay.
For example, 5 repetition is here. So we see that in the entire network, we have 5,000 collisions in the entire network for the entire scenarios.
Okay, taking out all the routing in between and so on. So just what
this
is
is
about? Okay.
MAC layer collision.
MAC layer only, yeah. So MAC layer from the ground to satellite.
Yes.
Not only for the ground satellite, not between the satellites.
No, ISL is point to point.
Okay, point to point. Okay, sorry.
So yes, this is the result we have here, and here is the delay. What happened is that with ISLs, we have a lesser delay for sure because we don't have to wait for the satellite to move to reach another ground station. So what happens is that this is like we have 50 seconds, and we have 450 seconds. So this is almost like very different curves, and this is the best benefit for employing ISLs. In fact, the delay is very low compared to the non-ISLs versions. Want to make the conclusion?
Well, to finish the presentation, after this we will present this live demo of FloRaSat. But the conclusion about the presentation is this new version of FloRaSat with the new modules and everything there is an improvement of the original version. Additionally, we also demonstrate the KeyMac is a simple repetition-based MEC protocol. But this, even if it's simple, it addresses some critical challenge in DTS IoT scenarios, only for transmit multiple times, especially with visibility problems and this kind of stuff. And as a future work, we think that we should focus on the development on a potential dedicated Mac sandbox. Even if we already were able to implement and integrate a new Mac protocol, I think that a new Mac sandbox, a dedicated Mac sandbox, will facilitate the implementation, the integration without a lot of work. Well, of course, all this improvement make FloRaSat 2 a comprehensive end-to-end simulation platform.
It's because I just want to mention at the beginning we have like another map layer, which is the LoRa map layer classic, the LoRa one, and
LoRa one.
Yeah,
Okay.
LoRa one, yes. And so when I implemented the KMax, there is like a kind of sandbox. This is something that we can work with, but it's not as developed as the routing one. So we need to improve it.
Mm-hmm. Well, I don't know if you have more question about the presentation, or we can pass to the execution.
The devices, they are only transmit, that do not receive anything. The devices on ground devices.
Yes, yeah.
And the satellites only receive, do not transmit anything except for the other, to the next satellite. Okay, or to the ground station.
No beacons, nothing.
Okay, just silent. Okay.
Yeah.
Okay.
A more general basic question. So there are other routing protocols and MAC protocols that could be used in the simulation.
It's more easy to integrate more another routing algorithms. But the Mac, I mean, we were able to implement, but it's more work because we need to make more changes in other parts of the code.
But the situation is dynamic there. They're moving all the time, so you make a decision, you don't have more time to use that decision. Be careful.
Interesting. KMac, just to be clear, the transmission windows, are they periodic or they are random?
Okay, yes. The fact is, we compute the transmission window depending on the parameters.
So they are not static, they are dynamic.
For one scenario, they are static because we are. Yes, understand. But yes, this is static because at the beginning we set the parameter. We said, okay, everyone will use those parameters, and then we can compute the transmission window. And in the initial KMac, we have multiple transmission window.
Mm-hmm.
So I have one message that I would love to send. I will do it 5 times. I will wait like 10 minutes, and I will do another 5 times. I will wait 10 minutes, another 5 times to maximize the transmission possibilities.
But it can be adapted every 5 minutes.
But this is like in the configuration file, so I can.
Same visibility window for each of the device. Is this you use 5 times the same visibility window, right?
What is why visibility?
You put the coordinate parameters in the simulator, yes, or just configure the location of each.
Yes, so you can show.
And then maybe the simulator use the formal equations for.
Yes. So what happened is that
it's just a question.
No, it's good. It's like everything is computed as the simulation evolves. So at the beginning we set all the orbital parameters and everything, and when it moves, it checks if it can see someone. So it's like it's event based. So each time it moves, it says, okay, no, I'm here, and the device says, okay, I'm here. Oh, okay, maybe we can connect. No, the password is too bad. Okay, then they move and they say, okay, we can connect. So they can compute a route, then do the stuff.
Okay. Can I pass to the?
Yes.
Okay.
Yeah.
Well, basically, okay.
created three scenarios. This is the parameters that we can set. Let me share the presentation here. Okay. We have two general parameters. That is the time simulation. That is the time all the simulation. We also have the time first packet. This is the in which time the device will transmit all the device the same packet. And we also have the time to the next packet. And for it, we can see the different values.
That's the window.
Yeah, that's the window. So this means that each device will transmit each 50 seconds a new packet, or in the scenario 2, each 100 seconds, and so on.
Well, you have 25 packets over there. That's the total time divided by the window.
Yes.
So a short time simulation. Okay.
Yeah. Basically, just to have a very fast results, very quick results. Okay. We also have another parameter, which is the ignore interference. This basically a parameter is more only just to see how it works on the execution of the simulation, but the text allows the detection or no detection of the collisions at the satellite. So if the value is false, it will not detect collisions. So
all the time will be received, no capture, nothing.
Yeah. And we also have the transmission power. This is a parameter that we set, and basically it depends that set the transmission or power of the devices. And that's something that Additionally, we also have some metrics that we recorded. Basically, we have 5 metrics. The first one is the number of packets that we sent, since you mentioned it before. Since in this case, we have 30 devices. In the three scenarios, we have 30 devices. So basically, we need to multiply the number of windows transmission by the number of devices. So in the first the second metric will be the number of packets received by the destination. We also have the number of packets received by the correct satellite calculated from the routing algorithm, and also the number of packets discarded due to the SAT not belongs to the route, and finally the number of collisions. Let me open here. Oh. Yep.
I tried this simulator just once, but I take some suggestions.
Yeah, it's a little hard to work with .NET, but
yes, we are currently working on.
It's a nice tool.
Yes, we are currently working on we are working on a first introduction, some a kind of documentation to launch your first simulation, because when you open it the first time, you don't know what you can do with it.
But an example.
Yes, but we are writing some documentation during.
That's the idea.
This is the current idea.
I saw the videos on YouTube, but
there's another one. Yeah.
Well, basically, here
I tried just one. Once.
This parameter basically sets the duration of the simulation, which basically is the same value. For example, we have I think it's better if I touch it. Here, we are setting the time to the next packet, and this is the scenario 1. So we also have this parameter here. Here we are saying that the satellites will ignore the interference. Will not ignore the interference.
This is a default.
That's the default value.
One question about that. So that's, for example, as the CSMA collision detection and stuff. So the idea will be test that feature of some protocol. No? It's not realistic, but it kind of implements some realism. No, that's the idea of that.
I mean, it is. You can study with that. If you have some orthogonality in the uplink, so that if no collision happens, then that would be the flag that you want to that we're going to set, I guess. I mean, the real simulation there would be to simulate the capture effect for LoRa at that point. So interference is actually guided by the capture effect.
The capture effect, okay.
And the other parameter that we can set is the transmission power from the devices. So here I set it to 14 dBm. Sorry, I'm not pronouncing correctly the unit, but 14 dBm. And also here we can set other parameters, maybe the speed factor.
So 14 dBm is enough to arrive there, or what would make a difference with the 8 dBm scenario?
Yeah, actually that's something that we will see in the second scenario, because 14 dBm is enough to reach the satellite, but 8 dBm, according to the simulation, there are some cases where it's not enough to reach the satellite. So that's why we will, if we compare the scenario 2 and the scenario 3, they only differ in the transmission power. So we will see a different amount of message received, a different amount of message that reach the destination. So if we execute, I mean, it's kind of, yeah. It's kind of hard to use Subnet, because, especially if you are using Mac, because they have another processor, ARM, so there is a problem with some access, some pointers. So basically, we have a 30 device and 20 ground station and a constellation of 66 satellites. We can see here all on the device. We have 20 device, we have 20 ground station, 30 device, and 66 satellites. And basically the idea of this is transmit, all the device will transmit to the nearest ground station at the same time. And in this case, there is an interference, so the satellite will detect some collisions cases, especially for the device that are very close. And I think that's all we can see at the execution. They are initializing the modules. We can see here how since there is no all the device transmit at the same time, there are several collision cases, and all device transmit to the nearest satellite. So there will be more collisions. But even with that, there are some cases that are able to transmit to the nearest ground station. There are some devices that are able to transmit the packet. So after that, the simulation will still running until we reach the 50 second, and then start again.
New packets and so on.
New packets will so on and so on. We can see that here.
You can see the satellite are moving.
Yeah.
Each time they are updating the position, so they can. And this is 50 seconds, so maybe
It starts the process to transmit
to generate the packet and then to transmit.
But there are some cases of collision and so on. But well, if we finish the simulation, we can make an express run. It will run very, very fast, but we won't able. We can see no animation. We can see the animation there. But here, this execution. No, it's not. But this execution will create a file that basically is here. Let me update. Let me update the folder. Basically, it creates a file where that stores all the metrics that we set at the beginning. In this case, we have these metrics, and for example, we can see the number of packets. Packet sense. Let me grab that. And here, let me filter to the devices. And here we can see that all devices transmit 50 times, according to what we expected. And we also have the number of packets received.
Do you have the specific information for each IT device?
Yes,
Nice.
it's important. It's very. So in this way, we have all these values covered. Just we have, for example, that the first ground station only receives one, and so on. And of course, that we can export this data to a file and make a proper analyze. But here, in this table, I synthesize basically the message that that the sum of all the values. And here we found that there was 600 message received by the ground stations, and also since this constellation is fully connected, is also the same value that the message that are received by the correct satellite. I mean, by the satellite from the routing path.
Can you zoom there?
Yeah.
My eyes are not itching. Okay, there we go.
And we also have another amount, which is basically the number of packets discarded. This represents that the message that are received by other satellites that doesn't belong to the route. And
discarded at the map layer.
Yeah, and we also have the number of collisions. That since in this case the detection of collision is activated, so we have several collisions as we saw in the
So the number of collisions. So you transmitted 500 packets.
Yeah.
And you get 2,000.
Yeah, this occurs because the device transmits to all the satellites.
So the same satellite. How do you count the collisions? In fact, that's the question. So the thing is, one. So you have 3 packets arriving. One collision between 2 of this and 2 and this pair, and this pair.
Okay. The fact is, you never receive 2 packets at the same time. So you receive the first one, then the second one, and then the power is compared to see if you can receive or not the second one.
Yeah.
And then if the third one you receive, same thing.
Yeah.
So if it's less, it's counted as a collision for this one.
Yes.
And if it's more than the other, it's counted as a collision for this one. So if you have 3 packets arriving at the same satellite at the same time, you have 3 collisions.
So the kind. Okay.
Yes. So the number of collision is the number of packets that is not received due to another one that is received at the same time.
Yeah, but you're.
But because what Alex said, one satellite can receive 10 packets at the same time. Because imagine the satellite in.
Yeah, but the thing is, the same satellite on the side will receive the same 10, for example. So you double the number of collisions for the same packet.
Exactly.
Yes.
Okay, that's
the same packet can
one single transmission can generate 10 collisions that are received by the satellite.
And the simulator is realistic in terms of the power. So you put 14 dBm. So if you reduce the power, you will have less collisions.
Yeah, this is what happens
in the scenario number 2.
Okay.
Because in this scenario we set it that only 8 dBm.
And 8 dBm is enough to transmit to the.
Just in some cases.
No?
Just in some cases. For example, we can see here that in the scenario 2.
But the thing is, you are not receiving collision because they ignore collision.
Yeah. But I can set it and we can check if you want.
Yeah, but that's good. And the propagation, the radio is like free space for
yes.
uniform.
Channel model is free space channel model, so very simply. So this is where I think Tomás channel model can definitely play a role and compare how it compares.
Just noise, right?
Yes, just noise.
I mean, this is of Antonio direction, so it should kind of work with them to implement.
Exactly. And it will be super nice to see how the Tomás model compares with the free space channel. Is it optimistic, pessimistic, and so on? And then we also use the antenna models that are provided by Omnet++. There are some antenna models that you can use, so you can change the gain pattern.
Right now they are using omnidirectional antenna. So but there is a model on iNet that you can set.
But then for the transmitter and the receiver, so you can
I think we have
they have both sides.
But the thing is, the pattern is supposed that the same power is received on the whole surface, or they just
there is the angle, right? The angle of arrival.
So in the center, 14 dBm, so
Yes.
okay.
The fact is, something good with
I
Omnet
remember,
is,
but I remember it was
yes,
that-
but it's very modular. So
Yeah.
the fact is, you can add whatever you want. Like, we can change anything if we keep the same architecture.
that improved. Okay, from the time where I left. Nice.
Yeah, but I want to finish. Basically, we have the second scenario and the third one, where both, if you see here, they have basically the same condition, but they differ in the power of transmission. And if we execute the scenario number 2, we will see. Just some seconds, please.
It's faster on Linux.
Yeah. We basically will see that there is the satellite won't detect collision, so they will receive all the message. Oh, sorry. With the elbow.
It's not a simulator.
No.
It's a computer.
Yeah, we can see here that there is no collision in this case, and it transmits. However, if we run until the end of the if we run until the end and we analyze the same metrics that we analyzed before, we will have these values that basically in this case there will only be 750 packets sent. But since that the power transmission is only 8 dBm, a lot of packets are lost because it's not enough to reach the satellite.
So because of packet loss there, we get 750 and you receive 406. The discard, so the difference, but what difference? 39.
Yeah, and this is different in the third scenario where it's 14 dBm, and there is also
you have one extra 3. How many? 759. You add the received ones and the discarded ones. It's not 750. They're just a different. That's one difference.
No. Sorry.
So if you add the received ones and the discarded ones,
yep,
it's 3 more.
This is not the discarded one. This is the
discarded one. The 353. And
Yeah.
the one is on 406. So 3, if you add them, that doesn't not fit.
No.
It's always something.
It's always by the same of the
Because
device
you
transmission.
can reach 10 satellites, but not the good one.
Mhm.
Okay, that's the point. So
Yes, so it's not the.
Yeah,
it's
especially in this case because it's not energy. The energy is not enough to reach all the satellites.
So I didn't get it. What is the reason? The numbers don't match?
Because since you can see, for example, that one device can transmit to 5 satellites at the same time, but the energy is not enough to reach all the satellites, so that's why it's not.
So on the case on the side, you get the 750 and you have a lot of discarded packets. Anyway, the 750, yeah, right.
Yeah, because those satellites that receive those packets doesn't belong to the group.
And there is a way to exclude that, because that will be kind of strange if you present it like you receive 200% of, I don't know.
No, this is not.
Because
No.
if you have a destination, you should receive 100%. But it's received by another one. It's not your target, no?
It's not at the destination. Those are the packets.
Anywhere.
Those are the packets received at the destination.
Okay.
Yes.
This is only on the beginning,
Yes.
only the beginning
On
of
the
the
satellite.
station, on the satellite,
Okay.
on the first satellite, because only if and device transmit to all to 10 satellites close, only one satellite will process.
You have the broadcast.
A question related to the transmission power. So you could easily implement like a transmission control instead, because you did scenarios with different transmission.
Yeah, I mean this is.
But you could have a dynamic approach as the one.
As I presented yesterday.
It is easy to do something like that.
I want a dynamic approach.
Yeah,
So instead of fixed power, could you implement like a, let's say, dynamic
for
power
each device?
For transmission power, you mean?
Yes.
For each
it
device?
should be very easy. Actually, I mean, I only said it here in the configuration file.
Yeah.
but there is some function that you can set values in real time in execution of net.
So it could be compared like a CTP.
Yeah, we
FTP
can
with
put
the ones that.
maybe some conditions in the code.
Yes.
Yeah.
Which are the conditions you need for that?
Yeah.
Which are the conditions?
Sorry.
Yeah.
Like my need condition is need to calculate the distance between the device and the satellite.
Okay.
And if this condition respect the maximum value of the transmit power.
Okay.
And then the device can choose.
That should be quite easy.
You need to respect this value because in my case, if you look at the visibility windows, we have some times that you need more than dBm to transmit in that position. So you need to respect the maximum value.
But in that case, if you have multiple satellites on top of your head, you need to already choose which is the distance, which is the one you're going to use so you compute the distance, right?
Yeah. I consider just one satellite right now.
Right. That will be something. If we code it in FloRaSat, we will need to decide what to do in that case.
Yeah, it's nice.
If you have multiple, you choose the closest one and then you do the computation or not. I don't know.
Or choose the longest one and be sure to reach.
Or be best. Maybe you already have nice.
Maybe an intelligent strategy that the device can decide. It's much better in terms of energy. Energy consumption of battery.
Yeah, and the strategy is interesting already because if you choose the farthest away one that Alex said, okay, you maximize the chance of getting to everyone, but you also increase the collision rate because you will also interfere the other ones. But if you choose the closest one, maybe you just pinpoint the closest, and you're weaker because if you use that one, then you lose everything. Yeah. But so I think the trade-off there is very interesting to see what happens.
That's basically all the presentation. I know you have more
So
questions.
related to that, the energy consumption is a metric that you could get easily, or it needs to be programmed as well?
I mean, we can put here, basically, if it is static, you can multiply by the...
But maybe you want to comment about the module we're cooperating with other guys.
We started to work with another, from Brazil, I think.
Yes.
And they were developed a model to measure the consume of the energy, and they they sent a paper where they analyze and how they measure the consumption in FloRaSat, and they fully integrated, and now we are trying to work together and see how this.
That's a per packet power consumption. Or there's also something else?
It's only on device level.
Yes.
Yeah.
But you compute it per packet. You don't have any other thing which adds consumption. Just a question. Or you have base consumption plus the per packet? Or...
No, we don't have that detail yet because they only send us the paper.
Yes,
there
I don't
is
know
no
what
implementation.
We're waiting for them to send the code, but I mean, of course, having like a background load it should be something straightforward to also. Yeah, I think this model from these guys is going to be useful because we are also going to study interesting, because also you can consider when the device is going to wake up to send something or not and so on.
I think you have a power balance in the satellites that you are recharging your batteries, when you are exposed to the sun or not, and I know that includes that kind of calculation.
No, this model is only for the device as far as I understand.
For the device.
For the around. Yes.
Okay.
Yeah, the satellites are, Kineis, all this company, what they typically do, they over-design it in terms of energy. So they are over-dimensioned, which is also not good. Maybe there is room for it to say, guys, you can squeeze this a bit and optimize a bit more.
But if they didn't have space, you should.
Yes, exactly.
Too far away, too expensive, not to over-design.
Right.
Okay.
Yeah. And additionally, the previous professor that came from Brazil, so I didn't remember, the previous professor some weeks ago,
Professor
Eduardo.
He mentioned that he has that we can also try to integrate because he managed real information of satellites, so we can also try to integrate and have a more precise model to measure energy and all that stuff.
Yeah.
By the way, how it works in case you have traces? So it allows you to put logs there, like read it, and because this is event based, no?
Yes.
So,
What do you mean by traces? Like traces from real vision? You are thinking in your
exactly.
data set?
This data set or another data set is
No, we don't take data set as input. I mean, this is a simulator and runs in non-real time, so it's event-based. Yes.
At the end, if you want to create your own data set, you need to run the simulation.
Okay, so that professor what was saying was different.
Yeah, it's just give some initial conditions of some detailed techniques about the implementation, about the
Realistic.
more
configuration of
realistic.
like-
Yeah.
Okay. Great. We have like some, sorry about the question that's like very initials, but
No, yeah.
we hope to make better questions. At least
No,
in the future.
If you're, for this experiments, you're considering a parabolic or monopole antenna.
Do you remember which model
I
you have there?
Because from where I've
Check.
previously,
Maybe you can check it.
Yeah, yeah,
we
I
have,
can check
I
it.
You
think
remember?
it can be omni.
I also wanted to ask the same
To me, it
question.
was an omni. How is the name?
Yeah, for example, Marcos was using patch antennas.
Yeah, let me.
Lo das en el punto net, creo que se puede buscar.
Sí, aquí lo tengo.
Ah, claro, ahí, perfecto.
We can see in the simulation here in the tree of
Because that can
models.
also be optimized later on in the simulator.
For sure.
In the
I
satellite.
mean, everything that has to do with the physical layer, for us, it's like a quick black box, like with simplified models. This is why I definitely think that what you guys do is perfect, because for us, it's just a black box. Maybe you can go into that black box and fine tune things.
Yep, here is a constant gain antenna. That's the type that we are using.
Constant gain.
Yep.
That is in the satellite,
Yeah,
Alex, right?
it's in the satellite. Yeah.
17, 12 dB.
And can I ask you quickly to show, because this is being recorded, so can you show to Antonio what is the propagation model?
The
The
propagation.
channel model.
If it's easy to show.
Where we compute the attenuation and the power and
Principle,
the
yeah.
physical layer part.
Yeah, I think it should be in the medium, right?
It should be the medium, probably.
There
Yes.
is.
Por eso, que el estudiante
There is
hizo
a lot of
bastante-
medium here. I remember.
We're testing Alex to the extreme here. So to see if he remembers where are the models.
Yes, no, it's a really labyrinth.
Ya,
Propagation.
Propagation, that's one.
Ahí está. Ahí está propagation speed.
okay, so Antonio.
It's in the LoRa medium module. Antonio.
Yeah, also Camila is listening anyway, so they will work together. Thank you.
Yeah, you should check those. I think it's path loss. There is path loss,
Yeah.
background noise. These are the models you want to check.
Yeah, but alpha 2 is the free space.
Yes,
Yes.
that is it's in free space.
Okay.
That is the models you want
Yeah,
to look
because
at.
that's 2 and that's free space.
Yes,
And then background noise and analog model. These are the models you want to look at.
great. Yes.
I think that propagation, this is be careful because propagation in satellite terms is the orbital propagation, is the movement of the satellite, not the signal propagation.
Okay.
So just beware when you see propagation, maybe it's not really the channel model.
By the way, I use Optus when I was a student, and I use it to vapor communication. And one of the issues we had with the propagation model was like the model applies for all the simulation. For example, in this case, it means you choose a model, and maybe it's the same model for the ground to satellite and the satellite to satellite.
Mm-hmm.
So at least at that time it was very difficult to, let's say, run it with two propagation model, and then we were so in most of the, I don't know if you are aware of veins or all those, they use one propagation model for all the links, even if they know there is a vehicle in the middle, which is a very bad simulation. So this is probably also now I'm thinking a challenge, because the idea will be ideal to have different propagation models for inter-satellite communication than for satellite to ground.
Yes, of course.
But I know if this is the same free space.
In this case, it is the same.
Yeah. So I think this will be also another interesting point to
Yes.
look at.
To have two different channel models, one for ISL.
free space, so not ISLs.
Right, so we're using free space for the device to the satellite, but then for the ISL, it's just a point-to-point link, very simplistic one at the moment.
No propagation.
No propagation. We never lost a packet because of physical layer issues on the ISL link.
Okay. Interesting, because that's also something I would say valid to change.
Yeah.
Exactly.
And to
Yes.
study. Yeah.
Yes.
Yeah.
But you have to control something. You start with a simple model in order to say, okay, who's responsible here? for the loss, and then you start to add some.
No. Yeah, the simulator is great, but I'm looking to opportunities want to say something else.
Yeah.
This is why, I mean, if you see that we are simulating, one of the ideas with FloRaSat was simulate the system, the complete system, end to end. I mean, from the packet to the satellite to the ground station and everything. In order to achieve such a broad scope, we simplify a lot of things on the way.
Mm-hmm.
And these simplifications are independent research opportunity on each of them. Right? So you can dive into one of these boxes and work. These other guys that Alex mentioned were looking on the energy modules. If you want to look into the channel model, people can look into that. And the thing is, you have a system level simulator that can understand which is the impact on the system level.
And so far, all of these we have seen like more like satellites, but we have not looked at the receiver itself. If the receiver itself has some, let's say, difference between if it's in the water or in the desert of Sahara or whatever, the receiver itself is just a receiver?
You mean the gateway, the antenna?
The ground station, you call it.
The ground station, yes. Yeah. Maybe, Alex, if you want, you can right-click on one of the ground stations and show what is inside. So this is a bit of what you see inside of the ground station.
Okay.
And every element in Omnet++ have different modules inside. Mm-hmm. Maybe we don't have the time to go in details on each of these. But yeah, so inside each of the elements, you can dive in and see what boxes are in there. And so
like that's interesting because, for example, I don't know, I've studied a lot of over-wire communication. Let's say I will use ground stations that are buoys, and then you include, let's say, the effects of I don't know, tides, which is and that could lead to, let's say, impact of water, whatever, into the satellite communication.
If you can describe your behavior as a C++ routine, then you can plan it in here.
When I was a student, I did it. Okay. But then I changed to a hands-on stuff with real experiment.
Okay.
But I did a lot of stuff on Omnet a long time ago.
Yeah. I mean, the good thing about this is that you can study like huge constellations and play with different systems very easily. That is the game, right? Of course, it's not the real experiment, but you can make.
Yeah, but in my case, the real experiment were possible, so we were kind of make more sense to go and do experiment. And in this case, it's not necessarily possible because we don't have satellite or many satellites. Great, thank you.
Thank you, Alex and Manuel. It was very, very good.